Hi guys, let's revise our lesson and then we're gonna take new lesson. So here our lesson describing Earth's atmosphere. We took it and we finished it and we answered the questions. So today we're gonna just revise it and then we're gonna take lesson 2, which is energy transfer in the troposphere, in the atmosphere. Okay, so let's start by video.
Visualizing the layers of the atmosphere. Earth's atmosphere is made up of 5 layers. Each layer is unique in composition and temperature. The layer you're most familiar with is the troposphere, the layer closest to Earth's surface. In the troposphere, the temperature decreases as altitude increases. When you fly in a plane, you might be flying at the top of the troposphere. Above the troposphere is the stratosphere. Air temperature increases with altitude here. Most of Earth's ozone layer is found in the stratosphere. Approximately 50 kilometers to 100 kilometers above Earth is the mesosphere. Like the troposphere, air temperature decreases with altitude. The thermosphere stretches between about 100 kilometers and 500 kilometers above Earth. Temperatures rise with altitude to more than 1,000 degrees Celsius. The outermost layer is the exosphere. In the exosphere, gas molecules can be exchanged between atmosphere and space. Dividing the troposphere, stratosphere, mesosphere, and thermosphere are areas called the tropopause, stratopause, and mesopause.
Yes, okay guys, so now we know the layers of the atmosphere, and here in this video, here the man mentioned that there are 5 layers. Okay, let's take a look here. Layers of atmosphere. So now who can say them? Yes, from the closest to the Earth. Yes guys, troposphere, stratosphere, yes, mesosphere, thermosphere, and exosphere. Good job. Okay. So here, what are the 4 main layers of the atmosphere? Look here, 4. Why 4? Because in some books mention that the thermosphere and exosphere the same layer. Okay, so stratosphere, from the beginning, troposphere, stratosphere, mesosphere, and then thermosphere and exosphere in the same layer. And here, what are the characteristics of each layer? Here our essential question. Earth's atmosphere is divided into 4 main layers based upon change in temperature. Layers of the atmosphere, like we said, the troposphere and the stratosphere and the mesosphere, thermosphere and the exosphere, the outermost. Yes, here the layers. The first one is troposphere. Yes, troposphere, lowest layer of the atmosphere closest to Earth. You live here. Tropo means turning or changing. There is more changing in this layer than any other. Weather occur here. Here, very important. Weather occur where? Here in the troposphere. Shallowest layer or thinnest contain almost all the mass of the atmosphere. It is 16 kilometers thick at equator and less than 9 kilometers thick at poles. As altitude increase, temperature decrease, like you watched in the video. Okay, and then stratosphere. This is the second layer of the atmosphere. Here reaches from troposphere to about 50 kilometers above the surface of Earth. Strato here means layer of spread out. Ozone layer is here. And the ozone layer is very, very important. And I asked you inside the class why the ozone layer is very important. So why? Remember, it protects living things from ultraviolet radiation from the sun. Here, jets often fly here because it is calm. As altitude increase, temperature here increase. Here the opposite happens. And remember that in the troposphere, here the temperature decrease when the altitude increase. But here in the stratosphere, when the altitude increase, the temperature also increase. Okay. Mesosphere, third layer. Meso means middle. Reach from 50 km to 80 km above Earth's surface. Protects Earth's surface from being hit by meteorites. Here a chunk of stone emits from space, but some still get through. A shooting star is a trail of hot, glowing gases, and throw it leaves behind in the mesosphere. Here about the temperature also, I heard the relationship between temperature and altitude. As altitude increase, temperature decrease. So this layer like troposphere, the first layer. So the first layer like the third one. Okay. Okay, and then thermosphere, outermost layer of our atmosphere, reaches from 80 km above Earth's surface into outer space. There is no definite upper limit. Thermo means heat, thickest layer. You would not feel warm here. You have to find out why. Search. As altitude increase, temperature increase. Has two other layers. This one, thermosphere. Thermosphere has another layer called ionosphere. Lower layer of the thermosphere reaches from about 80 km to 400 km above Earth's surface. Energy from the sun causes gas molecules here to become electrically charged particles. Radio waves above all ions back to Earth. Makes signals travel much farther at night. Auroras happens here, the display colors, if you remember I said it, near the poles because of the ionosphere. These are brilliant streaks of light in night skies. Exosphere. Exosphere here, exo means outer. So is the outer portion of the thermosphere. So that's why here this book mentioned that there are 4 layers, not 5. Okay, if we consider exosphere part of the thermosphere. Okay, so here reached from about 400 kilometers outward for thousands of kilometers. Space shuttles and satellites orbit Earth here. Yes, so here remember Earth's atmosphere is divided into 4 main layers based upon changes in temperature, like we said. So here the graph. Okay, so here this is quiz. Try to answer it. And here the essential question: what are 4 main layers like we said? Yes, troposphere, stratosphere, mesosphere, and thermosphere. And thermosphere has layer which is exosphere, right? And inside also the thermosphere there is ionosphere. So you can say 4 or 5. So if you said 5, so you have to mention exosphere. We said 4, you will mention here the 4 layers, but you have to mention the thermosphere has exosphere. Okay. What are the characteristics of each layer? Troposphere, weather happen here, we live here, thinnest layer, lowest layer. Stratosphere, ozone layer, and jet streams are here. Mesosphere, coldest layer, shooting stars happen here. According to thermosphere, thickest, hottest layer. Yes, and that's it about our lesson. Here we're gonna take new lesson. So look here, guys. Here your quiz. This is the online quiz. So I will assign yes, here. So here your names to know that all of you have the online quiz. Okay, and here please do it. Okay, yes, let's do the due date. Okay, I will receive it. Okay, Monday. Okay, no problem. Next Monday. Okay. Okay, so you have to do your online quiz. Okay. So let's take a look here. Our new lesson here is energy transfer in the atmosphere. So what do you think? What type of energy that transfer in the atmosphere layers or in the atmosphere? What do you think? Yes, of course, thermal energy. Yes. So here, energy from the sun. Here, the sun's energy reaches Earth through the process of radiation. So here, of course, the energy or the heat from the sun reach to the Earth's surface during a process called radiation. So let's watch this video. Here you will know everything about energy transfer in the atmosphere. Here we are in chapter 12, lesson 2.
Hey guys, Mr. Klein here. We are talking about Chapter 12, Lesson 2, Energy Transfer in the Atmosphere. The second of the lessons in this chapter we'll cover. It's a bit of a time machine, traveling back in time to some concepts we talked about in 6th grade physical science, and one subject we talked about in 7th grade life science. Let's go ahead and get started. 2 questions we're going to be answering by the end of this lesson. One is, how does energy transfer from the sun to the earth and the atmosphere? And the other one are, how are air circulation patterns within the atmosphere created? And this has to do with the transfer of energy. So let's go ahead and get started. Now, radiation is the transfer of energy by electromagnetic waves. If 6th grade, this is where we go back there. Remember the electromagnetic spectrum, where we go from radio waves all the way at one end, the longest waves all the way to X-rays and gamma rays on the opposite end. And these all have electromagnetism, so they have electric properties and they also have magnetic properties. And the ones we're talking about in this lesson I've shaded in red, and we're looking at light particles, photons, with the voltage of about 1/100th of a volt all the way to 100 volts. In this range is the infrared, the visible spectrum, and the ultraviolet. Within the visible spectrum, of course, we see the colors red, orange, yellow, green, blue, indigo, and violet, Roy G. Biv. And then below, red, slower than red on the infrared, on the visible spectrum is infrared, which is this right here, and then faster than violet is ultraviolet. So that's what we're talking about right there. And that's the transfer of energy by these electromagnetic waves. Radiation, as we'll talk about later, actually does not need a physical surface to bounce off of, which allows heat to travel through a vacuum, which is a really good thing because the sun is the source of our heat. And however, most of it is actually invisible light. And this is the case because that's the light that we see, but piggybacking on top of it is, of course, ultraviolet and infrared rays. The sun emits other rays and stuff, but that tends to get reflected by Earth's magnetic field. Now, so let's actually define what we're talking about with these ultraviolet and infrared rays. Now, ultraviolet rays have shorter wavelengths than visible light and can cause sunburn and skin cancer. That's one of the reasons why you go out. When you go out in the summer, you get a sunburn. It's not so much the light actually shining on; it's the ultraviolet radiation hitting your skin and heating it up. And on the other hand, at the other end of the spectrum, rather, we have infrared radiation. Infrared radiation will have longer wavelengths than visible light, and we think about that as heat. The heat that you feel if you turn on a heater is actually infrared radiation generating from the heater. Not like if you have a fan blowing hot air, but rather you have one of those conductive heaters that when you turn it on, it buzzes, bzzz, and then you see like the wires turn red and things like that. That is infrared radiation being generated. Okay, so that's the type of energy being radiated throughout the sun. The sun, of course, radiates it because it doesn't need a medium or molecules to bounce off of, which is really important, like I said. Now, energy on Earth. Now, does the sun actually receive, us on the ground, 100% of the energy that's passed off the Earth, from the sun to the Earth? No. Okay, actually, a lot of it gets blocked out. If we look at this diagram, 100% of the 100% we get, only about half of it actually hits the ground. 20% of it hits water vapor and dust and gets absorbed. 4% by clouds. 17% of the Earth's of the light that energy that the sun sends actually gets reflected off by the clouds, and then 6% the surface bounces off itself. Now, like I just said, 20% is absorbed by gases and particles in the atmosphere. In addition of these gases, oxygen, ozone, and water vapor, they tend to absorb ultraviolet light, which is why the ozone layer is so important, because it absorbs this ultraviolet radiation before it hits us, which we all get, really lobstery, sunburn-looking things all the time, which if you've ever seen me out in the summer sun, me and my pasty white self gets mighty red because of this ultraviolet radiation. However, water and carbon dioxide absorb infrared radiation in the troposphere. If you remember from the last lesson, the troposphere is the lowest level of the atmosphere. Of course, above that is the stratosphere, then the mesosphere, then the thermosphere, and then the exosphere. But the troposphere is down at the bottom. Now, Earth's atmosphere and the surface of the sun will actually reflect about 30% of the sun's radiation that comes toward Earth. Okay, if we look at this right here, okay, 17.6, just about 23, just about 30%. Yeah, averaging a little bit. It'll go from there. But the bulk of it, 46%, is actually absorbed by the Earth itself on the ground, which is about 50%, like I just said. Okay, so the Earth's surface absorbs most of it. Darker things are more likely to absorb light and absorb radiation than lighter surfaces. That's why when you go to the beach, especially a white sand beach, it's a lot hotter whenever you put your hand over the surface, because rather than touching it, because the light, because it's light colored, it's bouncing off the sand. But if you go and you find like a dark colored sand or dark rock or dark mud, something like that, and you touch it, it'll be a lot warmer than a light colored one. So, let's talk about some other ways that Earth deals with energy transfer. And one is the balance of radiation. That's what ends up happening is the Earth tends to reflect off about as much as it takes in. And see, the reason why Earth's temperature remains stable as opposed to varying wildly like the moon, where it's really hot when the sun's facing it, and the dark side isn't facing the sun, so it's really, really cold, is because of the balance between the amount of radiation coming from the sun and the amount going out in Earth. And one of the ways that we have this is mainly through land, trees, and the ocean. Not only do they absorb, but they also bounce off solar radiation, mainly in the form of infrared radiation. If we were to take an infrared camera and go off Earth, we would see a whole ton of infrared radiation being actually kicked back toward the sun from the ground itself and the water. Okay, because so the Earth has these abilities to reflect it in order to keep the balance, because we don't want the planet to be too hot and too cold. As a result, life won't be able to sustain itself. We just want it just right, which is why astronomers, whenever we're looking for planets outside the solar system, look for what we call the Goldilocks zone, where it's not too hot, not too cold, it's just right. Those are the temperatures, that range of temperatures is what we think about as supporting life, because that's what we see right here on Earth. Now, one of the other things that it keeps Earth's temperature pretty much balanced is what we call the greenhouse effect. And later this year, when we talk about pollution and climate change and global warming, we'll talk about this in more detail. But let's talk about the basics. Okay, a greenhouse. That's the pictures you see at the bottom is that of a greenhouse. But essentially, a greenhouse works like this. It's a building covered either in glass or a translucent covering, which means it lets most light in, not all of it. And what happens is the glass allows sunlight into the greenhouse. So you get the visible light, you get the ultraviolet radiation, you get the infrared radiation. However, whenever the heat goes to bounce out, the glass prevents infrared radiation from escaping. As a result, a greenhouse is much warmer than it is on the outside. If you don't believe me, think about this. Oftentimes in the winter time, you can go into a greenhouse, especially if you're not around where we live in Louisiana, where my class is at. You can go into greenhouses when it's in the winter and it's below zero, and if you have a lot of sunlight, it'll be a lot warmer artificially than it is outside. But the easiest example we all know is in the summertime, especially here in Louisiana, where temperature gets up into the 90s Fahrenheit, or in the 30, 35, almost 40 range during the summer. What you'll oftentimes do is, if you see a car, and the car will be sitting out in the open during the summer, and so all the windows are glass, and so what happens is the light, the radiation from the sun goes in, and the sun generates all that stuff. Like I said, it goes into the interior of the car, but the glass blocks out the infrared radiation, which allows it to get warmer and warmer and warmer, which is why when you open up the door, it's, oh my god, it's so hot. And that's essentially the greenhouse effect in action in a car. Now, this takes place on a very large scale on Earth because of certain gases, water vapor and carbon dioxide mainly, and these gases essentially act like the glass in our greenhouse example. What these gases do is they'll actually block infrared radiation from escaping out into space, and as a result it keeps the Earth much warmer. And so that means that the Earth can stay warm at much less temperature than it has to if it did not have an atmosphere. So let's look at this. Okay, this is kind of the greenhouse effect in action. Okay, we know that the sun brings in radiation in terms of visible light at much less temperature than it has to if it did not have an atmosphere. So let's look at this. Okay, this is kind of the greenhouse effect in action. Okay, we know that the sun brings in radiation in terms of visible light, infrared light, and ultraviolet light. Okay, about half of it hits the surface, most of it gets absorbed. Some of it, greenhouse gases, will absorb some outgoing radiation. Okay, but a lot of it ends up getting kicked back out. That's what we saw in the example. And the greenhouse gases will keep this this infrared radiation, and it'll keep bouncing it around in the Earth. And because of that infrared radiation is bouncing around the Earth, that's heat that isn't escaping. Okay, so that's a greenhouse effect in action. It's essentially gases that keep infrared radiation on the Earth, keeping it nice and warm. Now, let's talk about thermal energy transfer. Okay, if you remember earlier in 6th grade, things like that, you might remember the 3 ways that heat is conducted, and we'll talk about a 4th one in a second. But one of them, of course, is radiation. Okay, radiation is when energy passes from one to the other without a connecting medium. Okay, this is an example from the sun to the Earth, or ultraviolet radiation bouncing out from the sun. The other one is conduction, where a heat source touches another molecule and heat is transferred. And the other one is the fluid movement of heated air. That's actually convection. Okay, so thermal energy always moves from objects with high temperature to lower. Okay, if you put a hot object in a refrigerator, it won't get cold as much as the refrigerator will actually get warmer, because the heat moves from higher to lower. If you're in class at our school during the winter time, whenever we have whenever the heaters are running, especially in the afternoon when it gets warm and you're like absolutely baking in classes, if you come into my science class, there's usually a breeze. And the reason why is I have the front door open into the hallway, and then I have the door into my courtyard open. And what's happening is we have a wind, a breeze flowing, rather, because what's happening is hot air from the hallway and in my classroom is flowing through the classroom out into the cooler courtyard. And as a result, heat always moves from high heat to low heat in order to reach an equilibrium. But because the Earth is really huge and it's really cool, you're never going to run out of heat. So that's why you always have that air flowing in there. Now, like I just showed you in the example, conduction is the transfer of thermal energy by the collisions between particles of matter. Heat is transferred when one molecule bounces into another. Now, when air heats up, it becomes less dense and rises, transferring its energy upward. That's because the atoms are moving around so quickly, they're not so much packed together. Okay, so energy always goes upward. Now, the transfer of thermal energy by the movement of matter from one place to the other is what we call convection. And a lot of the thermal energy transfer on Earth is actually through convection. A lot of your ovens are what we call convection ovens, because what happens, the reason why it bakes is because elements get really, really hot, and it heats up the air, and the air starts circulating, because that air circulates because of this movement from more dense to less dense, and so on and so forth, causes the temperature to rise throughout the entire area of the oven, causing it to bake. And the final one, which you might not have heard about, but that's okay, I'm going to talk to you about it for a second, is essentially what happens in the Earth whenever water changes phases from solid to liquid to gas. Okay, and actually when any substance changes from solid to liquid to gas, what we call latent heat is exchanged. Latent meaning heat that is stored. So when water melts from ice to liquid, latent heat is released. When water is heated up from liquid to water vapor, heat is released. When bits of water evaporate even at room temperature, because the molecules escape, latent heat is released. So the four types of temperature, four types of thermal energy we see, is one comes from the sun in the terms of radiation. But on Earth, what we have is conduction, which is where one warm molecule hits a cooler molecule and heat is transferred. Convection is when warm air rises and cold air drops to replace it. And latent heat is heat that's released whenever chemical changes due to the change in matter, states of matter, from solid to liquid, liquid to gas, so on and so forth. Now, let's talk about circulating air, since we did talk about convection. And a lot of weather, essentially all weather, is driven by this circulating air. And wind currents, which we'll talk about in the next lesson, has to do with this. When warm air is pushed upward because heat rises, cool air will sink to fill in the empty space left by the warm air. And like I talked about the example in my classroom, the warm air moving to cold air, warm to cold, creates air currents. Okay, air, and this has to do if you live in a mountain range out in South Louisiana where high ground is like 50 feet above sea level, not so much. But air tends to move upward near mountain ranges. What it'll do is the warm air will follow along the mountain to go over, and then cooler air will sink down, which will cause what we call mountain waves. It's essentially waves of wind that go over the mountain, creating what we call lenticular clouds, which we'll talk about later with the clouds. It's clouds that look like lenses in glasses. Now, circulating air will affect weather and climate around the world. And we will talk about what the difference between weather and climate also later on. But just to remember that weather is the local conditions where we're at right now. And where I'm at, where I'm sitting as I'm recording this, it is in the mid-60s because it's in the evening and we have rain, okay, in middle of this beginning of December is when I created this. Climate, however, is kind of the conditions of temperature and precipitation amounts over a long period of time. Where I'm at in South Louisiana, our winters tend to be cool and damp with a lot of rain. So the weather conditions might not always match the climate. Okay. However, our summers are, of course, oppressively hot and humid, even though we might have some days that because of a rain shower it might be cooler. So that's the difference between weather and climate. We'll talk about it in more detail from there. Now, let's talk about stability. Stability is the property of the atmosphere that describes whether circulating air motions will be strong or weak. If you don't have a lot of difference in temperature, the air will be very stable. Because there isn't a big difference in temperature, air won't be moving around. Okay, when air is unstable, circulating motions of the air are strong. So if there's a big difference in temperature, especially when a weather front's pushing through, and we'll talk about this in more detail. When a cold front passes through, what happens is you'll have warm air on one side of the front, you have cold air on the other side. And that difference between the two, in that short space, is an area of instability, because like a couple of miles it might be 70 degrees, a couple of miles away it might be 50. The 20-degree difference in the change of the air temperature causes a lot of air to move around. And because of the air is always moving around, that's what happens, is how storms and stuff form. Now, in general, warm air will rise, cool air will go down to replace it. Sometimes, though, we have an imbalance in the stability, and sometimes we might have a layer of warm air sitting on top. And that's what we call a temperature inversion. In mountain valleys, you'll see this a lot, but occasionally where we're at in Louisiana, we'll see it especially in the wintertime. Whenever a lower pressure system that is near the surface might be really cold, and it's traveling along, but a couple thousand feet above, the temperature is much more stable and it's actually much warmer. And we have an inversion where the temperature increases as altitude decreases. In fact, I remember one time when I was in college and I was taking flight school. Yes, that's another fact about me. We were getting ready for our flight plan and stuff, and we were getting the temperature and things like that. And whenever we went to go up on our flight, on the runway, it was about 48 degrees. And at about 300 feet, we were barely in the air after taking off, the temperature jumped to about 70. It was a big difference. And the reason why was there was a layer of cold air right at the surface, but only a couple hundred feet above, it was much warmer. And this was because of air masses and stuff moving on each other. When we talk about weather fronts and stuff, we'll get into more detail. But you just need to know that there are times where stability is influenced by outside forces. And here's a good example of this right here. This is in Scotland, and where we see a temperature inversion going on. And so I want to graphically show you what we're talking about here. If you notice right here, you see the smoke rising, but it's sitting, okay, and the fog sitting right there. Why is that the case? Because there's a temperature inversion going on. Okay, it's very cool right here. Right here it's warm, and above there it's cooler. Because if you remember, the higher you go up in the troposphere, the cooler it gets. So let's look at this. Okay, if we notice, the temperature inversion is right at the surface. It's cold, and if you notice, at this line right here is where the smoke and the fog sit at, and that's where this warmer air is sitting at. Okay, this warmer air is sitting right here, and it's blocking the cold air from moving around. Okay, so the cold air can warm, but because it's not as warm as this, it gets bouncing back down, so that's why it stays cool. But of course, above this warmer air is the colder air of the standard troposphere, where it gets cooler on the way up. So as a result, the cold air can't escape from that, rather than the normal pattern of it being cold here, cold air being here, but cooler air and colder air going on from that. So let's go ahead and let's wrap this up. Temperature inversion sometimes, especially in areas around Los Angeles, California, Mexico City, and places like that, will prevent air from mixing, and so it stays nice and stratified. And as a result, it can trap pollution close to the Earth's surface, which can perform a health hazard for some people. Okay, so let's go ahead and let's wrap up this lesson. By the end of this lesson, you would have been able to answer these two questions. One, how does energy transfer from the sun to the Earth and the atmosphere? Well, essentially, primary transfer of energy from the sun to the Earth is through radiation. And I spent the last 8 to 10 minutes talking about this last question. How are air circulation patterns within the atmosphere created? Well, they're created because heat transfers through conduction, convection, and radiation. Okay, all those heat air. And as the air gets heated, it rises because of a difference in temperature. The warm air rises, the cool air goes down to replace its circulating air. And this circulation of air is what we call wind. And we talk about the wind currents and stuff in this next lesson. So there you go. Energy transfer in the atmosphere, not the most exciting subject. I know you believe that. But if you have any questions or comments, feel free to let me know. Thanks for watching.